All right. Well, we give people a few minutes to get in. Fortunately, there were quite a few difficulties trying to get Hangouts going on the computer I wanted to use. So we're going to start a little bit late, but that's okay. All right. First, let me make sure that I can properly share my Fusion 360 desktop. Josh, you said you can hear me. Can you see my desktop okay? I'm getting ready to draw some stuff in Sketcher. Extruding some things. Okay. So, well, welcome everybody. Get rid of this sketch here. This was originally intended to be just for some guys in my makerspace, but accidentally a lot of other people got invited, so that's kind of extra fun. Basically what I was going to go over was some basic part creation and then programming it to be CNC routed on a CNC machine like you'd find in a makerspace, a basic 3-axis mill, router, or something like that. And we also might go over a little bit of laser cam in Fusion 360 if we have time. It's very similar to a CNC machine, and it works great. I really like it a lot. But all right, so the first thing that I normally do when I am getting ready to make a part for CAM is I'll start a project and say CAM class 1. And then I'm going to open the project up, and I'm going to say File, New Design, and right off, I'm going to save my design. So it's block. Right. So now, when I'll hide this. When I'm in my model space here, you'll notice the y-axis, the x-axis, and if we look at the cube, we see top. This is fairly important. When it makes your life a little bit easier when you're drawing specifically something to be machined. Later you'll see that you don't necessarily have to follow this, but it does make things a little bit easier. So what I'm going to do is just going to create a sketch and create it here, and I'm going to create it in my positive coordinates, just because that's where I like to draw. And choose R for a normal stretch rectangle, and let me give it some size, so I'll make it 200 by 250. And to give it some geometry that's fun, I'm going to make some 1/4" holes. You notice I only dimensioned the first hole. And then what I'm going to do after that, so I hit escape, say equal, click the hole I want to make it equal to first. And now all of those holes are equal to this first hole. I want to make those 1/4" holes because I'm going to drill with a 1/4" end mill. And we'll give them some quick dimensions so they make sense. Obviously, this isn't super critical. I don't even care about these. These are fine. All right, so now I'm going to do some other geometry. Do big circle and a bigger circle and a couple little ones. We'll make something fun to machine. And then a bigger form. So I'm going to make these into a pocket. And I'm going to make these circles tie into each other with the tangent constraint. You notice the first one that I click is the one that moves. So that's good to remember. And I'm just going to trim these out. I'm just hitting T to activate the trim command. To the wrong parts of the circle. We'll delete these. All right, so now we have some drilled holes, a fun hole to make into a pocket, and a fun hole to bore. So now I'm going to say stop sketch, and I'm going to hit Q for press pull. The other way to do that is to just hit the press pull command from the top there, and I'm going to drag this up. And you notice that all of the geometry I created in my sketch gets left out of this, and only the field that I clicked in is what gets picked. So if I delete that and I pick that, and hold down Q, I can reverse that stuff. And normally I machine 3/4 inch MDF. That's what I almost always machine. So we'll just make this 3/4 of an inch thick. And enter. And then I wanted to make this a pocket. So I'm going to bring this sketch back. Hit Q again. And we'll raise that up. Call it 5 millimeters. 5 millimeters is fine. All right. So now I have an interesting part to machine. Let me check something real quick here. Okay. So the next step, what we want to do is we want to create this body into a component. So I'm going to drop this down, right click on the body, say create components from bodies, and now this is here. We could have done that initially, and then this sketch actually would be tied to the component automatically. If I try and drag it down, it gives me a fun error. Fusion's full of fun errors. So for now, we'll just ignore that. The one other thing that I want to do, and that I do a lot of the time when I'm prepping things for CAM, is I create another component and I call that the stock. And what this lets me do is it lets me turn on the stock simulation in the CAM so I can see that everything's being machined properly, that my cut depths are proper and everything like that. So what I'm going to do for that is I'm just going to mock up a sheet of MDF. So we'll right click on the CAM block, the root of the model tree here, say new component. I'm going to call this stock. And I'm going to give the original component a name too. We'll just call that pocket part. One of my early on CAD teachers taught me that features are like pets. If you care about them, you give them a name. And with a part like this where we have 2 features in one sketch, it's not such a big deal. But when you get into a part like this, where we have loads of parts and loads of sketches, things start mattering. And when you're trying to refer back to, oh, what plane did I want to use? And everything's just plane 1, 2, 3, 4, 5, 1, 1, things get hairy. So always name your features if you care about them, just like your pets. All right. So I'm going to activate my stock with the radio button, and we'll create a new sketch. Click on it. And I'm going to leave my other part active, and then I'm going to say project, and I'm just going to pick, no, didn't want to do that. Pick my outer lines. This is one way to do it. And then I'm going to say offset, and we'll offset this 15 millimeters. A round number. And the only reason I'm doing this necessarily is so I can see the outline get cut out. A lot of times what I'll do is I will make a stock part as the size of the entire machine bed or the entire sheet that I'm cutting. But for right now, just for demonstration purposes, we're just going to make this a little bit bigger than our part. And then say Q. Oh, wait, not yet. Turn off my original part here. I'm going to get rid of these lines because they're just going to get in my way when I try to pull my stock up. Turn our original part back on. And you notice it's not trying to join to my original part because we are in 2 different stock. Oh, okay. Somebody just told me that you guys can't see the pop-ups. That's not good. Nope, you can't. All right, 1 second. We'll just say entire screen. I love that. Okay, now you guys should be able to see the pop-ups. For some reason, CAD applications are weird, and every one of these windows comes up as a whole different window instead of just being part of the application. So sometimes they work, sometimes they don't. And I remember that coming up in a different Fusion Hangout that I was watching and not actually giving. All right, so notice that in the operation, it comes up as new body, and it doesn't ask me specifically to join, and that is because these are two different components. And that is an important part of Fusion, is to understand the difference between bodies, components, and component groups. And if you guys want me to do a separate session on that, I would be happy to. It is deeply important to the hierarchy structure of how Fusion works. So we're going to make a new body, and the direction is going to be one side, and the extents, I'm going to say 2. And click on the top face of this. So they're exactly the same. So I don't have to remember that I made my part 19.05 millimeters, which is 3/4 of an inch. Okay, so that's it. That's all I have to do to create a 3D model to machine in Fusion 360. The next step is we're going to move from the model environment to the CAM environment. So we'll do the model drop down, and in all of these fun different tools that Fusion has, we'll grab the CAM environment. Okay, so in CAM, there's a few gotchas. And these took me a little while to find because initially when you first open up the CAM environment, all you want to do is make a toolpath that cuts something and see the tool simulation because it's awesome looking, right? Well, if you just initially go in here and you say, I'm going to face something, I say stock, all of this, you hit OK. Well, for one, that's not the face that I wanted to select. And for two, oh, that's nothing like what I wanted. That's because we didn't go through and we didn't tell Fusion how our part is set up in the machine. This is very important. This is probably the main difference between Fusion and a lot of the more user-friendly CAM packages out there like CamBam or any of the Vectric products like vCarve Pro or Cut2D, where they walk you through the setup dialog before they even let you see the part. Fusion expects you to understand a little bit about how CAM tools are set up, and it just will let you crash all and burn all over the place. So the first thing I'm going to do is I'm going to delete this setup that it created. And we're going to go in and we're going to say new setup. All right. So the first thing I see is my part triad is not oriented the way that I would like to orient it. In a typical 3-axis mill, router, laser, what have you, the bed is set up so that the X and Y are the flat part of your bed, and Z is straight up. So it's straight up through the tool. 3D printers are the same way. And this is one of the benefits that you guys coming from 3D printers will have, is the routers and mills are set up exactly the same as far as coordinate systems. One of the things that bugs me about Fusion is these tabs are out of order. It wants you to set up your stock with just a couple of millimeters of excess stock on all of the sides. And that's almost never how your part is going to come. And as soon as you go through and set up this orientation and then reselect your stock, it just resets everything. So in my opinion, these tabs should be reoriented. You should be setting up your stock first. And in our case, we're going to set up our stock using a solid part. That's why we created this outside part that's bigger than our inside part. So I'm, instead of saying a fixed size box, which is a box that you specifically tell it how big your stock is, 280 in the X, 20 in the Y, which isn't right because our coordinate system's off, or 230 in the Z, or a relative size box, which is how it brings the part in and it just adds 1 millimeter to the biggest part in the setup, or a fixed or relative size cylinder, which is what you would use for turning things or sometimes milling. I like to have a model of my solid stock, and I work from solid. So stock solid, click my part. Notice that these are 2 different colors, so my part isn't actually defined as the stock. And I go back in here, and now I'm going to say that my work coordinate orientation is not my model orientation, and I want to select from one of these options. A lot of times selecting the Z-axis and the Y-axis is easiest. Sometimes you don't have access to the Y-axis if everything is curvature, or the Z-axis. If everything's curvy, you won't maybe have something that's easy to select. So let's say select the X and Y axes. So the first thing it comes up is says X. This is my X-axis on my machine. My Y-axis will be oriented to this edge. And I am going to say that my origin is the bottom left corner of the part, because it's just the easiest way to think about it. But notice that my Z is still pointing down, so I need to flip the X-axis. It moves the triad over here. Let's put it back where I want it. Okay, so this is saying that the bottom left-hand corner, it is X0, Y0, and the top of my stock is Z0. So the bottom of my tool will be touching the top of my stock when I touch off Z0. And for my model, I'm gonna click that. You don't always have to do that. I haven't seen any real benefit to do it or not to do it. The one box that's left in here is Fixture. Now, this is very useful if you have a modeled specific tool, or say a mill vise or drill press vise or something like that. You have clamps in there, and you've got all of those modeled. You can say Fixture, and it will build that into its tool paths, and it will avoid it. But we don't have that, so we're not going to worry about it. All right, so now we have our little tool origin triad down here. We have setup 2, since it created setup 1 when I made that bad tool path. And we're going to do a new operation. And for now, I'm going to turn off my stock part because I don't need it. And we will start by, first thing we need to do is define some tools that we're going to use. So in the tool library, I have new libraries that I set up using the new library button. And I set up some mills and drills for my benchtop mill. And I set up some mills for my router. And the difference between those two is my mill has a top speed of 3,000 RPMs. My router has a top speed of 24,000 RPMs. So I have very different feeds and speeds between the two machines. Even though I might be using some of the same tools, the chip load and everything will be very different between them. So I set up 2 different libraries for them. Today, let's set up a whole new one. So in the cloud, CAM cut lib. And I'm going to create a new mill tool. So let's start in the cutter. And we're going to use a flat end mill. And my units that I'm going to use for my flat end mill, I'm going to use inches because that's how I've always machined everything. Inch tools are easier for me to buy. And when I was setting up feed rates, it's just easier for me to think in standard units per time versus millimeters per time. Almost all of my end mills end up being 2-flute end mills because I route a lot of things and I just don't cut a lot of steel. And I'm going to use a 1/4 inch end mill. So we'll say 0.25 inches. My shaft diameter is going to be consistent because I typically use carbide tooling, which has a consistent shaft diameter. You very rarely have a reduced shank shaft. And my flute length will be 0.75 inches. My shoulder length will be 1 inch. My overall length is 1.5 inches. For the shaft, since I don't have any specific tool holders in mind, I don't have, and I'm not trying to create any sort of avoidance, I just leave this out. Same for holder. The feeds and speeds are where it's important. So for my machine, if I'm cutting MDF, I'm typically running about 24,000 RPMs. I'm just running flat out, as fast as the spindle will go. My cutting feed rate, I run at 100 inches a minute. And I'm going to turn my lead in and lead out feed rate slightly down. Lead in, I'll show you guys in a second what that does. And my ramping feed rate, since this is just MDF, I'm going to run this at 60 inches a minute. It's nice and soft. Yeah, we'll do the plunge at 40. This gives me a feed rate of 0.02 of an inch per tooth, which should give me a moderate chip load. According to some of the tool diagrams out there, we can run this a lot harder, but my machine usually tops out about 100 inches a minute, and it's plenty fast for me. So I'm going to hit OK. And then I'm going to create one more tool since we had a drill in there. Make a drill. Again, we're going to say 2 flutes in inches. Those holes were 1/4 inch. Tip angle, almost every drill that you're typically going to find is 118 degrees. You might occasionally find 135 degrees and a couple other specialty tip degrees. But most drills that you find at a hardware store are 118 degrees. Feed and speed. I run my drills on my router a little slower. We'll run this at 15,000 RPMs. And we'll do 30 inch per minute plunge. Okay, so now I have a 1/4 inch end mill and a 1/4 inch drill. And let's make one more. Two. I'm going to make a 3/8 inch end mill. Actually, I don't think that will show what I want to show. So never mind. Let's not waste time here. Okay, so now we have a 1/4 inch end mill, 1/4 inch drill. This will do everything that we want it to do. So to start out, I'm going to start out by drilling my part. So for the drilling toolpath, click drilling. Select the tool that we just created. So in CAM cut lib, we have a 1/4 inch drill. Fusion has a ton of sample end mills and tools and drills. What I found though is unless you're running a high-end machining center, most of the tool information stored in these samples isn't suitable for running on a hobby level machine. So we'll notice that when it brought in my tool, it populated my spindle speed, my surface speed, my plunge rate, my feed per revolution, and my retract rate. But I defined all of those in inches per minute. Well, it always defaults to meters per minute, millimeters per minute, millimeters per rev, and I just can't think like that. So that is why I go into the tool dialog box and I define all of that stuff ahead of time, because it just works better for me. It's perfectly suitable to change those things here. That's why they're here, but I just have trouble thinking in those numbers. So, all right. So the next step is the geometry box. We can do two different things. We can either select faces or select center points. This is very, very handy. If you ever want to program something very quickly and you don't necessarily need the whole geometry to understand where you're putting things, and you just want to put a field of points out there where you want your holes, you can just select points. We made the whole faces, so we're going to use those. So we can select this. You can check this and it will select all of the holes of the same diameter. Since I know I want to drill all of those holes, this checkbox is super useful. For a lot of things, though, it is dangerous because who knows, you might have a hole that you don't necessarily want to drill the same as all of them. Maybe one of these is a blind hole, and I selected that, forgot about it, and just scrapped a part. So for a lot of things, especially in my professional life, I will just go ahead and select all of the holes individually so I know. For this, we'll do that too. I'll show you guys both. You can order by depth. You can optimize the order. Almost always, I just leave optimize the order good and call it that. The heights is an interesting one. One thing to note is a lot of times, especially on hobby machines, benchtop mills, your Z is very limited. And if you're using something like a Jacob's chuck that's a little long, it's really very possible that when you set up these retract planes, you're going to run out of machine travel. And since most of us are running machines with stepper motors, the machine's not going to know. It's going to jog up, think that it did this almost 20 millimeter clearance above the part, and it's just going to start running into things. I have rapided through a few parts now because I just didn't take that into account. So it's very important to always make sure that you have proper clearance over your part when you're setting up these clearance planes. For the most part, these numbers will work kind of out of the box. So what it does is it sets up a retract height or a clearance height that's 10 millimeters over the 5 millimeter retract height. The retract height is where it will wrap it out of the hole to, and then it will, as it's moving, it will jog up to that top after the entire part's done, and then start on the next operation. The top height, you can say whole top. I like to know exactly where I am defining my top. So I like to say selection, and then I select the top of my part. Same for bottom height. I've just been burned by this too many times by letting the CAM software figure out what it wants to do. And then with drilling holes, it's important to note where the bottom of the tool is and what the CAM software thinks is the bottom of the tool. With drill bits, it's going to be wherever you set Z0, and most of us set it from the drill tip. Well, if you drill the drill down to the bottom of the part with the drill tip, you won't have a hole that goes all the way through your part. So it's important to pay attention to, one, what's underneath your part. Can you drill all the way through it? If it's on a CNC router that has a spoil board, sure, you can. If it's on a mill machining fixture that has clearance pocketed out underneath it so that you can drill all the way through, sure, you can. If it's the flat face of your mill table that's nice cast iron, maybe you don't want to drill through that part. So that's important to know what you're doing. For this, I'm going to say drill tip through bottom, and I'm going to give it 2 millimeters of breakout depth. So it's actually going to go through the part probably about 3.5 millimeters with the included angle of the drill tip. And the last thing is just the drilling cycle. So there's a number of different types of drilling cycles that we can do in this. Rapid out is what it defaults to. If you're doing any type of wood, rapid out's probably fine, unless you have a small drill bit or you've got wood that packs a lot, like pine. Chip breaking is good for aluminum, where you get real long stringy chips. Deep drilling is what you would want if you're drilling through wood that packs. What that does is it rapids all the way out, and that'll clear out all of your flutes on your drill. You can do all kinds of interesting tapping cycles, boring cycles, back boring, pocket milling, bore milling, thread milling, and probing all through this dialog. I haven't done most of those because I don't have tool or machines that are capable of anything like that at the moment. But it's nice to know that these are all available to you should you hit a point in life where you get to seriously upgrade your CNC toolbox. So now I have my drill path all set to go. And the last step is to simulate it, see how it looks. So in the simulate dialog box, we can display the tool, or we can turn the tool off and just have a dot floating around. You can display the tool path that it's going to take or turn that off. And the important thing for me is to give a stock simulation. So we can have it stop on collision with a fixture or something like that. Or we can just let it run through the part. So if you look, that's going quite a bit through the part. So if that was my mill table, I'd be pretty upset. But the sheet of spoil board MDF I have on my machine, I don't really care about. I just want to know that my drill went all the way through my part. That's the most important thing for me. Okay, so now we know how to drill. Next step that's interesting that we're going to do is 2D adaptive clearing. So we can do two different things to make this pocket. We can do adaptive clearing, which does a pretty interesting toolpath. Some people don't like adaptive toolpaths because they do weird stuff. Or we could do a 2D pocket, which has a very traditional path. It's not necessarily as fast or as nice to the tool, but it looks good, and it looks like how somebody would hand program it. I really like the adaptive clearing paths, so that's what we're going to do. So just like we did before, I'm going to go in, I'm going to pick my quarter inch flat end mill. Notice again, all of my feeds and speeds are in millimeters per unit. For my pocket selection, I'm going to pick the bottom of my pocket. Stock contours and tool orientation really aren't needed. Tool orientation is very important for anything that has more than 3 axes. Or if you are doing something strange where the tool orientation doesn't match what your setup's going to be, you have a right angle head or something like that. But for this, tool orientation isn't needed. Again, we're going to go through and we're going to set up the retract height, stock top, top height. I'm going to leave top height at stock top. This time for bottom height, I'm going to say selection. I'm going to pick the bottom of my pocket. And then the last one is the really important one. Because if we just let this go the way it is right now, let it calculate, you notice that it takes almost 15 millimeter depth of cut. It just goes through and it clears out all that stock in a single pass. Let's do the simulation. So it's going to spiral in. It's going to side mill all that stock out. Now, if you have a super rigid machine and you're comfortable taking that heavy of a depth of cut, and something like MDF, you might be able to do it. My machine would probably handle it fine, but some of the smaller machines like a Shapeoko or an Ox, doing something like this is going to cause all kinds of interesting flex in your machine. It'll show you your weak points, that's for sure. So the way to fix that, we'll go back into Tuning Adaptive. And in the last one for linking, in passes, sorry. In passes, we're going to select multiple depths. And we will say that we want to do 3 millimeter step down. 3 millimeter is half of the tool diameter of the quarter inch end mill that we're using. A lot of people like to use that as a rule of thumb. On my machine, I have quite a bit of rigidity. I like to use the full tool diameter, and sometimes even a little more. Sometimes I'll run my stock at 0.3 or 0.4 millimeter, or 0.3 or 0.4 inches depth of cut. Stock to leave, I'm not going to leave any stock to leave, not this time. This is useful if you want to do a fast roughing pass and then come back and do a slower, nicer finishing pass to get a nice finish cut. Check hangouts, make sure things are still rolling good. Okay. So we're going to uncheck that. Smoothing. Smoothing is handy if you have a CNC controller that doesn't have a lot of memory or is kind of affected by running a ton of lines of G code. This is very useful when you're running a machine that's controlled by something like Machine Kit while it's on a BeagleBone Black, because there's some headroom that you run into with the BeagleBone. If you're running a CNC machine that's controlled by an x86 controller like Mach 3 or Linux CNC, it's not an issue. It can be a huge issue with older FANUC controllers, though, because they have a very small amount of memory. So what smoothing does is it takes, well, you can't move my mouse very much, but it takes extra movements out of the code and kind of cleans them up a little bit. So I like turning smoothing on. And feed optimization is another one that reduces the amount of feed rate changes in the pass. So it's a lot nicer to cutters. A lot of times cutters don't like you changing feeds throughout the pass. It does bad things to them. In the linking, this is useful if you have multiple paths that you're going to link together. Most of this I just leave default, except for the ramp type. In MDF, a 2-degree helix is okay. I'm going to step it up to a 3-degree helix to ramp that down a little bit faster. In aluminum, I like to do a 1.5 or 2-degree helix though, so it's nice and smooth and gives me a nice clean cut as I'm going in with a flat bottom. The other thing that we can do is we can do a pre-drill where we just go drill a hole real quick and then it will start in that hole. Or you can do a plunge where it just buries the end mill into the part. I don't like plunging if I can avoid it, even in wood. So we're going to hit OK. So now we have a ton more passes, a ton more work to do, but it's going to be much nicer on our tool. Let's speed it up a little bit. So we notice we're taking a much smaller depth of cut through this. So it'll take a little bit more time, but we are more likely to have an accurate pocket by doing this. Real quick, I'm going to show you what the difference between 2D adaptive and 2D pocket would be. I'm not going to spend a lot of time talking about it. I'm just going to show you what the difference in the tool paths looks like. All right, so the 2D adaptive, we do this nice spiral motion, clean out this, and then we come over here and we clean this out. In the pocket, we do this, we follow the contours of the pocket for the whole path. So we helix in just like in the adaptive. But we end up having this abrupt stop right here. And in that stop, we end up cutting full depth in the end mill. In wood, it's not such a big deal. In metals, end mills really don't like that. So we're going to close that out real quick. The last thing that we're going to do before we cut our part out is we'll do a 2D contour. So to do a 2D contour, basically all we're going to do is we're going to cut this part out. But when we get done cutting this part out, we're going to be left with a plug in here. That's one of our problems. The other problem is it's an inside cut. So it's important to note which side of the stock you're cutting on when you are setting this up. It's actually fairly obvious in this one. The tool will be on the inside here. A lot of times it's not this plane though. We pick this one. Because of where the arrow ended up, it's pretty obvious again. But in some of the geometries, it's not that clear. My examples didn't work. So one of the things that we're going to do is we're going to add some tabs. We want the tabs to be on the bottom. And what these tabs will do is they will hold our stock in place as it's being cut. So it doesn't jam our cutter or fly out and hit somebody or anything like that. Give it a 3mm tab height since we're cutting wood, quote unquote. Heights are good. Again, I'm going to tell it that I want my bottom to be the bottom of the part. we're going to climb mill. So this means is the cutter is rotating into the stock. It's pulling the cutter into the stock rather than conventional milling, which pushes the cutter away. Gives a much nicer finish. We're going to do multiple depths again. I'm going to say a 3mm step down. And again, I'm going to turn on smoothing and feed optimization. Both of those, the defaults have always seemed to work perfectly fine for me. In this one, I'm going to turn on my lead and entry. And I'm going to give them a little bit of, or my lead in and lead out. I'm going to give them a bigger radius. This is very nice when you are cutting your part so that you don't end up with lines where you end up cutting in and cutting out. Okay. We're going to simulate it. Play. So you notice it has this lead in move and lead out move. And then we end up having these tabs right here, and those tabs hold our part in, and then I just use a Dremel usually to cut those out at the end. All right. So then the last thing that we're going to do, and because I want to show you guys the laser paths, we're going to say that we're going to use a laser to cut this out. Normally, in any real-world application, I would cut this out again with the end mill because it's the tool that I'm using. But because I want to show you guys the laser, we're going to do that. So for me, I have a CO2 laser that I use Fusion occasionally to generate paths for. I'm not lucky enough to have a water jet in my garage. So I'm going to pick laser cutting. I'm going to say through and auto. These different cut modes are nice for machines that use quality settings to determine how fast they cut. With my machine, I use millimeters per minute, so I always just pick through auto. I haven't tried the etch or vaporize mode yet. I'm curious to try them, but I just haven't tried it yet. The kerf width is something that's kind of awesome. Most laser softwares that I have encountered just think that the kerf width is a negligible amount. But if you're trying to do anything that's tightly fit together, like finger groove boxes, or I really run into it when I'm making things for open builds parts, and I want a really, really tight fit for the eccentrics. So I have to set a kerf width on those. And the kerf width I usually use for my laser and something like birch plywood is 0.2 millimeters. That seems to work pretty good. It gives me a good press fit on the things that I care about. In the feed box, you can do two different things. You can say the machine uses quality, and then this cutting mode matters, or you can use machine uses feeds. My machine uses feeds. I cut at 10 millimeters a second. I think it's 600 millimeters a minute is the feed rate that I cut in. I have this all written down somewhere so I don't have to remember it. My lead in and lead out feed rate, that is the same thing that we saw here, where it's leading in or leading into the cut with a little radius and then leading back out. Just leave them all the same. For my geometry, I'm just going to pick this top surface up here. So my arrow's on the outside, so it's going to be cutting on the outside. We'll give it some tabs. One of the nice things that you can do with tabs is you can position them by distance, so that will evenly distribute them 80 millimeters apart, or however much you say, 100 millimeters. Or you can say at points. And then you can just say, I want a tab there, I want a tab there, I want a tab there, I want a tab there. That way you can place them where they make sense. A lot of times when you place them by distance, they end up in some awkward places that they're really hard to cut out. It just doesn't work very well. For a laser, a lot of you, probably this doesn't matter so much, these retract heights. So I just leave them 0. I don't have a z-axis on my laser. If you have a z-axis on your laser, these might matter a little bit, but for mine, they certainly don't. They are useful if you want to refocus between passes. That is handy. My machine, I have to do my compensation in computer because I have a smoothie-based laser. If you have a really nice laser that has a real CNC control on it, you might be able to do your cutter comp in your control. I have to do it in the computer. I'm going to compensate to the left, I think. We can tell in the stock simulation. And smoothing, again, is this G-code smoothing. I think this is much more apparent in something like a laser than in a CNC machine, so I always turn it on in the laser. And these are all default. I leave all these in default. The entry positions is an interesting one because with lasers, you end up with a heavy burn where it starts and stops. So if you wanted to specify that you were going to enter somewhere out here, you could use a point geometry for that. So hit OK. Simulate it. Look on the top, you can see a super narrow curve right there from my laser cut. You can see where it started and stopped for the tab. It's pretty handy. All right. So there's one more step. After we get all of this set up, we have to post-process our code so that we can turn it into G-code for our machine to read. So to do that, it depends on what kind of machine you have. If you have a machine with a tool changer, or you have a machine with tool change, G-code, and probing set up in it, or if you just have a normal machine that you have to hand change out all of your tools. For me, I have a machine that I have to change out every tool individually. So I post out all of my paths that use different tools individually. So I'm going to post out my drill. I post out these 3 individually, and then I'm going to post out my laser individually. Some machines, you could just right-click on here, post-process, and it'll send the M code to do your tool change, and all of that will just work. Mine is not one of those. So the first thing I'm going to do is I'm going to post-process my drill. It always gives me this error message. My CNC machine is set up with Linux CNC right now. So that uses the emc.cps post. Gives it a .ngNC program extension. And then I'm going to tell my machine that I want to output it into a folder that I'm going to create. I'm going to call it CAM cut. Open. All right. That's where it's outputting it to. So then I'll say CAM cut drill. And then in my comments, I just like to put down what tool I programmed that for. The units that you're programming it in is important. If your machine, for some reason, doesn't like to change units, it's important to tell it what kind of units you would like to work in. I like to leave it in whatever my document units were. So since I drew it in millimeters, it will output it in millimeters. The last thing is these are options for the different post processors that are available. This G28 will put a home command in. If for some reason your G2s and G3s use radius and not diameters, you need to specify. If you don't want to write your tool numbers, you can specify that here, etc., etc. It's very handy to have all of these options available to you should you need them. So we'll post this out. They'll ask me again where I want to save it. And then here's the code that it gives me. So it gives me the name of the program, the drill that I'm using, the tool number, the diameter, the taper, the Z-min that it's capable of, and then here's my G code for drilling my holes. Load that into Linux CNC and off I go, drilling some holes. Now I don't need to post out these twice, so I'm just going to pick the two paths that I want to use, right click on them, say post process. Change the name to CAM cut mill. Forgot that it won't let you use backslashes. We'll post this out. This one you can obviously see is quite a bit longer because we have all that adaptive code in it. But again, see name of the program, the comment of the program, what tool I'm using, and then the type of path that I'm doing. If I go down here, I can find the next path, which is the contour. And then the end of the program. Now, the last pass that I'm going to do is a different machine. So I'm going to post-process it with the smoothie.cps. We're going to say CAM cut laser, 100 watt CO2 laser. Now, this is super handy. I can set my etch power, my cut power, my laser tool number, all of that stuff right here. So for laser power, if I only want to use 80%, I'm going to say 0.8. I want to turn up my etch power so it burns a little hotter. I'm going to say 40%. If I need to turn on my laser with M3s and M5s, I turn it on and off with M3, M5. I can do that there. Again, tons of handy options in this. So we're going to post this out. And so here we go. Tool 1 turns on the laser, gives it a feed rate, sets it at 80%, and we burn through. You see it turning off at the tabs, turning on, off at a tab, on, off at a tab, on. Turns laser off at the end, home's out. It's pretty simple, pretty exciting stuff. So, I hope that you guys got something out of this. Sorry, I didn't have the Q&A turned on. I apparently disabled that somehow. But if you guys have any questions, or if you would like to see more of stuff like this, I would be happy to do this again, go over more Fusion things. And yeah, just let me know in either the Hangouts discussion or YouTube comments. Thanks.